Okay, since it has been a while, so let's quickly go over what we have learned from the beginning of this section. This section is our last section, which addresses the optimal dispatch of generators. So we learned some basic method for solving optimization problem. So typically it will take 3 steps. If you have a nonlinear function, you need to find the gradient vector del f. So the gradient vector need to be a 0. So which means you first narrow down your search to all stationary points, but which will include minimal point, maximal point, or saddle points. Minimal points means where you have a locally minimal function value or cost value. Maximal point, which means you have the highest cost compared to neighboring points. And the saddle points means in one direction is maximum, but in maybe another direction it will be minimum. So the second step is we want to make sure those points are minimum points by calculating the Hessian matrix. The Hessian matrix need to be a positive definite, which means locally this point will be smaller than neighboring points. And third step is we find really the smallest one among all the minimum points. So you see the idea is to narrow down to stationary points and the minimum points and really the global minimum point. Okay, so those are the step 1, 2, 3. But if your problem doesn't have very high dimension, so not many variables, so the number of stationary points or minimum points are not many, you can skip over the step 2. You only find the stationary points and calculate the function values at those points, and then simply find the smallest one. So that will be your final solution. So the key in this section will be calculating this gradient vector. F here is a cost function if you have no constraints. But if you also add constraints, you need to figure out a way to integrate your constraints into this cost function. So eventually you're going to calculate a extended cost function, which is called Lagrangian. Lagrangian will be a linear combination of the original cost function and also the price you're going to pay for violating those constraints. So the key will be still calculating the gradient vector, and then to find the stationary points, then we can find the really the minimal cost. So that's a basic idea. So we don't have to follow exactly this procedure, but the key will be to calculate the gradient vectors for either the original cost function or the extended cost function, which will be the Lagrangian function. Any questions? So that's a very quick overview about what we have learned so far. Then we move to a specific problem. So we start from the optimization with equality constraints only for economic dispatch of generation. So the Lagrangian function will be the original cost function integrating some equality constraints, each one multiplied by a lambda. Lambda is called Lagrangian multiplier, which is like a penalty or price you're going to pay for violating that constraint. So that constraint, each constraint is supposed to be held, which means the g here has to be 0. If it's not 0, non-zero value multiplied by the price, which will be the cost added to the Lagrangian function. That will increase your cost. So now the stationary points will be found for this L function, not for the original F function. So the idea will be starting from the 0 gradient vector and to make sure each element to be 0. And we just solve a number of equations. Finally, you will find all the stationary points, which make the L function to find the stationary point of the L function. And then we find which one will give you the minimal cost. So that will be the solution. So if we have a inequality constraints, so we'll add some inequality in this form. It will be like some u is not bigger than 0. It can be a 0 or less than 0. So if it's a 0, so if we know this u is exactly 0, we don't have to leave u in this category. We can simply just make u to join G, right? We can list U in G. So it will be considered equality constraints. If this one is negative, which means we shouldn't include this one in the gradient vector. So there will be two situations. So to address both situations, so we learn some method, which is called a KKT condition. The KKT condition says if you have to deal with equality constraints and inequality constraints, for inequality constraints, you only just need to solve those three together. You just add those three into your original equations from a 0 gradient vector of L. So the first two will be from original optimization with equality constraints, right? So we have partial L, partial X, partial L, partial lambda, so which are both elements from the 0 gradient vector of L. And the newly added item will be based on the KKT condition. The KKT condition says you just simply add those elements there. In our last lecture, we used some simple case to visualize what does this mean? How can we understand a little bit about how to prove this KKT condition, but which is not important. We only just need to know how to utilize this condition. So we simply just add those three items in the green rectangle into our original equations. If you have technique, you can solve the green and yellow one together. That will give you the candidate solutions. And then you check the function value. The smallest one will be your final solution. So if you deal with really high dimensional problem, usually you need to program some solver to solve the yellow and green equations or inequalities. But fortunately, we are dealing with lower dimensional problem, at least in this section. So we deal with economic dispatch. We don't have so many variables. So we only have the variables as many as the power plants, right? So such as we don't have to really program anything using this KKT condition. So which is equivalent, just go ahead. We just check two scenarios. The first scenario is if U is exactly 0. So which means you need to join this equality constraints. So mu need to be a positive. Mu is a Lagrange multiplier for inequality constraints. So if U is a negative, which means the solution is inside of the boundary defined by the inequality constraint. So we can cross off mu. We can cross off that item from the original Lagrangian function. So this is what we learn. If you feel this still confusing to you, when we go to the real example of a power system, it will be very clear. Okay, so now we are ready to talk about the power system. For power system, we need to construct the cost function for a power plant. So if we're talking about thermal power plant, the input will be the fuel, right? The fuel can be, we can treat the fuel is fed into this power plant at a certain speed. So every hour there will be a BTU. BTU is actually the British thermal unit, which is just a unit to measure how much fuel we feed into this power plant. So at this speed. So if we want to, the X is actually the output of generator. So if you want the generator to generate this power at this value, so that will be the speed we want to feel, we want to provide the fuel. Okay, so now if you want to increase to this generation, the fuel speed will be higher, right? That's pretty reasonable. And when we collect the data to draw the function, and we realize this function can be nonlinear, it may not be linear, which means there will be a certain limit. You cannot have this power plant to generate power infinitely high, right? At a certain level, will be the fuel will need a really high value, so you cannot afford that high value. So you have to solve there. So usually we concern certain region of the power output from some minimal output to the maximum output, and we model this part of the fuel input function, and so this is just the volume of the mass of the fuel. If you price this fuel, so you will have another unit, which is basically how much dollar amount you're going to spend to generate this power. So you will have a similar curve. So if the fuel price is constant, it's not like when your power output is higher than a certain value, your fuel price is significantly increased. So then for that case, you will see there's a two segment of curve. The second segment will have to suddenly increase the cost. But if we ignore this case, we only consider constant fuel price. So you will have the second curve. The second curve tells you the dollar amount per hour for any power output of the power plant. So the two curves are very similar because the difference only just a factor, which is the price of the fuel. So we are going to do optimization based on this curve. This only give you the price for a single power plant. We are going to collect such curves from all power plant, and we figure out which power plant generate how much to give out the minimal cost. As I said, we don't have to explore the entire curve. We only just focus on maybe one region of the curve, starting from the minimal output to the maximum output, such as we can narrow down a certain area. And for that area, segment of curve, we can use quadratic function to approximate it. If you want to try a higher order nonlinear function, that's fine, but usually quadratic function is good enough. Based on the project I have studied with utility companies, so usually they use quadratic functions. So for quadratic function, the cost function will have the constant item, which what does this constant item mean? It's basically just how this curve intersect with y, right? This y will be alpha, because this is the value when the p becomes 0. And then you have a linear item, you have a second order item. So we use the beta and gamma. So this is our quadratic cost function. Next one, we can calculate the derivative of this cost function with respect to the power output, which will be a linear function. So it will be this straight line. So x is still the output of power plant. The y is actually lambda. Lambda is actually it's basically just the physical meaning is the same as the Lagrange multiplier. But here, it just means the dollar amount per megawatt hour. That's the price of energy. So if you generate power at this value, that's this price. If you increase the output, usually the price will be higher. So based on this quadratic function, the price will linearly increase if you increase your output. So any question here? Okay. So let's move on. This is a table with data I used in the past with the utility power company. So those are real data. Those are data about the real power plants in Louisiana state. So the raw data that gave me have those values. Let me explain what they mean. So there are two power plants, two generators, A and B. The first raw is like fuel cost. Fuel cost will be the dollar amount per mega BTU. Okay, so you see the first unit is more expensive. The second unit is cheaper. Then the next two raw will be the maximal output and minimal output. For instance, the first unit can generate no more than 230 megawatt. If this unit is running, it need to generate at least 65 megawatt. So why do we have a lower limit for power plant? Because that's you cannot smoothly operate the power plant from a zero output until the maximum output. So there have to be a lower limit above which the power plant can be stable. Okay, lower than that, it would be very challenging for the power plant engineer to maintain the stability. So usually they require the minimal output. So this is also make, for example, the power system restoration be challenging. Because when you bring this, when you operate the system in the normal condition, most power plant will generate power between the lower limit and upper limit. Okay, so you only just need to make sure not violating those limits. That's exactly what we are dealing with in the economic dispatch. But think about you have blackout for the entire system, and you have to turn on power plant one by one. Okay, so once you decide to start any power plant, you need to quickly running or following certain ramping up curve until it can reach the minimal generation. So that one cannot be interrupted. You have to continually increasing the output until that minimal value. Then you have more flexibility to change the generation between this minimal and maximal. So usually the most challenging part will be starting the unit one by one, and keep in mind which unit is it has not reached the minimal output. So there will be a lot of dispatching challenges the engineer can face and operators. Okay, so those are the minimal output. And the next one is this value. So this value unit means you see this one doesn't depend on the power at all, right? They only tell every hour you need to utilize this much of a fuel. So what does this one mean? This one means just even when the power output of the power plant is zero, you still need to give this fuel. This is like a minimal fuel you need to provide it to keep the power plant run. Okay. And the following data will be S1, Y1, S2, Y2, S3, Y3. So each X is megawatt. So which means this simply just means P1. So this is P2, this is P3. And the Y1 is like every megawatt hour, how much fuel you're going to feed to the power plant. Okay, so let's talk about how to generate those curves. The first curve is about the fuel input in the unit of BTU per hour, and changing with the with power. So power is basically X, right? Those basically just X. The X, we can use the X value from those table. So take a look at this unit. So the next one we also need to find the incremental cost. So we need to figure out the Y value for each curve. So based on the unit, so the first curve has BTU per hour. The mean is fuel input. So how do we generate the points on this curve in order to find this curve? So BTU per hour can be simply calculated from, for example, let's see, if you multiply S and Y, so what is the unit at each point? So S1, S2, S3 just define 3 operating points. So at the first operating point, if you multiply S1 by Y1, so what is the unit? The unit will be a meg BTU per hour, right? That's exactly what is fuel input. So that means each point will be on the curve will be calculated by simply calculate the multiplication of S1, Y1. Then you have S2, Y2. Then you have S3, Y3. So that only give you 3 points, but you can fit into a quadratic curve. So you have the full curve. Okay, so next one. So how do we come up with this curve? So the second curve in the right box is similar to the first one. The difference is only a factor of the price of the fuel, right? So basically, we just multiply the first curve, each point on the first curve multiply by the price. So you will get a second curve. So this one is simply just SI times YI times this fuel cost and this fuel cost. That's second curve. So what is the third curve? The third curve by unit is for every megawatt hour energy, how much dollar amount you need to pay for it. So how do we come up with this number? It simply does a fuel cost multiplied by Y. Because fuel cost is actually the unit is dollar amount per MBTU, and Y is actually MBTU per energy, right? So it will be simply just this point. So you just utilize the Y1, Y2, and the Y3. So each one will be multiplied by the fuel cost. So we can draw the 3 curves. If you want, we only just draw 3 points on each curve. But if you want, you can fit those points into a quadratic curves for the first and second plot, and fit into a linear curve for the third one. And the next question is, where is this one? This one says no matter how much power you generate, you need to provide this MBTU fuel every hour. Okay, so that means this point. This point has a 0 output, and the unit value has unit of MBTU per hour. So basically, you just utilize those values here. Okay, so for the first curve, you have 4 points together. You can help you to find the closest quadratic function to fit it. Any question? All right. Okay, so this is the answer. I just utilize those formula to create those curves. So you can see the cost curve is there are 2 cost curves. This is unit A and unit B, and A is cost more dollars, right? Compare unit B, because the fuel cost for the power plant A is more expensive, is higher. And the second curve has incremental cost, so that the value of each point indicate the price, dollar amount per megawatt hour, the energy price, changing with the output. So that relationship is treated as linear in this slide. We have what else information we have not utilized from the slides. So we haven't utilized the minimal and the maximal output, right? So we need to highlight the region where we can operate the power plants. So each curve is bounded by a lower, is a P minimal and a P maximal. Similarly, for the both unit, they need to be operated within a certain region. Okay, beyond those limits, it will not be safe to this power plant. Okay, so now we can move to the formulation of the similes economic dispatch problem. We're going to dispatch NG, a number of generators to together support some low demand. We call it a PD. Each generator will have a cost. The fuel cost, we call them C1 to CNG. And for this simple problem, we ignore the loss of the network or anywhere, which means even connecting the power plant, we need really a power grid, right? But we ignore the energy delivery on the grid. So because we don't consider any loss. So there will be a power balance which says the input from all the power plant has to be equal to the output of the network going to the load. So we have only single equation. So that's simplified all the power flow equations. So we don't have to worry about the power flow analysis in this problem because we ignore the network. And also we ignore the generator limit. So which means there will be the formulation only has one equality constraint, which is the power balance. The input equals output. And there will be no inequality constraints. So we ignore the limits. Okay. And each cost of the power plant is formulated by quadratic function. To calculate total cost, we simply just add all the quadratic function together. So that will be the total cost of this system. And there's only just one equality constraint, which it will be left-hand side will be the total input, the right-hand side will be the total load. Okay, we are going to solve this problem. Compared to our general formulation, the first equation tell the cost function f. The second equation gave you a single equality constraints, right? So because there's only case, basically just single one. There's not many equality constraints, only just single one. Okay. All right, so we can utilize Lagrange multiplier method to solve this problem. So we have first a few variables as many as the power plants. And we add a single additional variable lambda. So this one model the penalty we're going to pay for violating that equality constraint. So later we'll see this lambda is exactly has exactly meaning the same meaning at incremental cost of the power plant. So the L function will be will have two items. The first item will be the total cost, basically just summation of all the quadratic cost function. The second is just, you see this one is just from the equality constraint, right? So this one is supposed to be 0 and multiplied by the penalty. So if this equation can hold, the lambda will be 0. You don't need to pay any penalty. If this equation does not hold, lambda will be non-zero. You need to pay some penalty. Okay, so next step we just we have this as the cost function with ng plus 1 variables, and we need to calculate the gradient vector of this dimension. So we have a partial L, partial P, Pi, and a partial L, partial lambda. Every one need to be 0. Then we can find the stationary points. Let's see the first type. So partial L, partial P, which is equal to partial C, partial P plus partial the second atom, partial P. And the second atom, there only just one atom, okay, having that P. So basically the second atom become negative lambda. So for this entire expression, if we talk about, like, for example, we consider P1, okay? P1 only appear once in this entire expression. So if we calculate partial derivative with respect to P1, that's lambda, right? Also have this negative sign. So that's why the second expression, second part become just -1. And the first part is basically just still the partial original cost function partial PI. Is this clear? Good. And second, so to calculate the partial cost and partial PI by partial PI, and because the total cost is actually summation of the cost of each individual power plant. If we calculate the partial derivative with respect to only just power plant number 1, we only just need to pick that cost function for power plant number 1. So which means we only need to calculate this conventional derivative, dCi by dPi. So Ci here is actually the only just cost for that power plant. And the Ci is actually from here. It's a quadratic function. What is PD is the low demand. Low demand. Okay. Yeah, low demand is constant. So when you calculate derivative, that becomes 0. So we're talking about how to find this partial derivative. This partial derivative become this the dCi by dPi. Ci is here, so it's a quadratic function. So to calculate the first order derivative with respect to pi, that's linear function. That's beta alpha will be 0 and 2 gamma p. And this is actually the partial derivative of this atom. And we know this equation need to hold, which means this one has to be equal to lambda. The first type of zero gradient vector elements means the derivative of each cost, power plant cost, with respect to the power plant output need to be exactly lambda. And that is same lambda for every power plant. It doesn't change with the I. The left-hand side has, the I can take any value from 1 to n, but the right-hand side is just single lambda. So what does this equation mean? This equation means all power plants need to operate at the same incremental cost, same lambda. From original incremental cost curve, right? So like go back to, for example, this example. So this is how each curve will be how the lambda change with pi. This is also lambda change with pi. So 2 units will have 2 different lambda. And the lambda is function of a p. So when you increase p, the lambda will increase. But from our derivation on that simple example, all the costs need to increase at the same speed of lambda. And from this equation, we immediately know if we know the price, we can find the value of the output. So this statement is actually pretty reasonable, because if you think about the statement, all units must operate at equal incremental cost. What does that mean? So even different units may have different cost function, different price incremental cost curve, but when they together support some load, they need to be operated at exactly same price, which is the equilibrium of the market or the dispatch. You cannot have any unit at this moment be more expensive than the other unit, right? If that's the case, you need to decrease its output, then you decrease its price. You think about 2 units, okay? So right now, operating the 2 units together to support the low demand PD. And the first unit is more expensive than the second unit. At this moment, the P1 plus P2 will be my load. And the price of the first unit is higher than the second unit. So the only thing I need to do as operator, I need to decrease the output of first unit, the more expensive unit, until the price go down to be the same as second unit. And meanwhile, I need to increase output of second unit. So finally, they reach an equilibrium. Then that will be the final dispatch. So this is like a necessary condition you have to satisfy. If you don't satisfy this condition, you haven't reached an equilibrium point or the stationary point of the problem. Is that clear? Okay. All right, so which means if we know the equal price, we'll know the solution. We'll know the how much output from each power plant. From a second type of element in the gradient vector. So we should simply just set the equality constraints. And since we already have a formula to calculate each PI, which is a function of the equal incremental price or cost, we just go ahead to plug in that PI. We replace PI by that formula. So then we have one equation. So in this equation, we have only one variable to solve, which is lambda. Everything else will be already given values, right? Including PD, which is the total load. Beta and gamma is actually the parameters from the original cost function. So you need to solve this equation for lambda. Okay, it's very simple. It's just a linear equation. I just go ahead to give you the answer. So this equation can be explicitly solved. If you have a not quadratic function, you have like third order, higher order nonlinear function to model the cost, and this function will become nonlinear. To solve this equation, you need some techniques such as the Gauss method or Newton-Raphson method. But for this case, we can go ahead to give a solution. It looks a little bit complex, but you can easily prove. You can just like for example, you can easily prove for the case of a 2 generator, right? You only have just P1, P2. So it'll be very, then you can extend the solution to more generator. All right, so we finish the solution of the problem. Because we know the lambda, we can directly calculate lambda by this formula. And we plug in the lambda back to the first one, so we'll calculate P. So it's done. So the final step will be just plug in the calculated P into the cost function, then we know the total cost. So to solve economic dispatch problem without any loss or generator limit, there are only just 3 steps you need to take. The first step is you use this formula to calculate lambda. That give you the incremental cost, which is required for every unit. Okay, then you plug this cost to the first formula to calculate PI, to know the output of each power plant. Then you calculate the total cost. Just step 1, 2, 3. You solve this problem. So later we may add generator limit or even transmission loss. We'll see those 3 steps still make sense. But definitely you have to do some iterations. You go from step 1 to step 3, then you come back to step 1. So just try and error. So finally you can find the solution. So those 3 steps are very important for economic dispatch. Let's use one example to explain what happened by those step 1, 2, 3. We have 3 thermal power plants with cost 1, C1, C2, C3. They're all modeled as quadratic function. So the constant value indicate the minimal cost, right? Even you don't generate any power, you still need to pay this price for the unit to operate. We hope the power output together can meet this demand, 800 megawatt. We ignore any line losses and the generator limit, and we want to find the optimal dispatch and also total cost. So how do we solve this problem? Right? Step 1, we just calculate the lambda because all the values are given. So here, this is alpha, right? This is beta, this is gamma. To calculate lambda, we don't need any alpha value. We just use the beta and the gamma. We can calculate this lambda. So you just go ahead to plug in the values. So 800 is from the demand. Each item will be the beta divided by 2 times gamma, right? It will be like beta divided by 2 times gamma. So in the on the denominator, you have summation of 1 over 2 times of gamma. And the answer will be $8.5 per megawatt hour. So you have 3 units at optimal dispatch. They need to operate at this price. They have to operate at this price. Then go to the step number 2. You just plug in this value into this formula. You can calculate P. Because beta and the gammas are different by units, so the P1, P2, P3 are all different. So P1 has output of 400 megawatt, P2 has 250, P3 is 150. The last step, calculate the cost. So that is $6,682.50 per hour. That's the price you're going to pay for the 3 units to generate the power for 800 megawatt. Okay, it's done. It's very simple, right? But we still want to understand what happened here. Why all units need to operate at exactly this equal incremental cost. So we can utilize the cost function curve or the incremental cost function curve to explain why this equilibrium is reached among those 3 power plants. So we calculate incremental cost. So this is lambda 1. Lambda 1 will be the first order derivative of the first cost function with respect to the output of first unit, right? So this is from here. It's a linear function. Then lambda 2. Lambda 2 is the second cost function. It's also a linear function. Then lambda 3. So if we don't require the 3 units together to provide 800 megawatt power at certain equilibrium condition, if we look into the cost for each individual unit, that's a linear function. So each function tells if you want to increase output, the price will go up. They all have different function of a price. So if we visualize those 3 price function, which will be the 3 straight line in this plot, X is P, is actually output of the power. Y is basically just price. So they have a linear price. And from our step 1, we know they have to operate at $8.5 per megawatt hour, which indicate a horizontal line at 8.5. So that line intersects with 3 linear curves at 3 points. So if you check those three intersection points, which will be 150, 250, and 400. So those are exactly the output of a 3 unit. And if you add them together, they give you 800, right? All right. So you see, even the 3 power plant have different curves for the price, but when they together to power the system load, they operate at exactly the same price. So that is why you cannot have any unit to be more expensive at this operating condition, because if they operate here, that's not equilibrium. If you ask this unit to operate at more expensive condition, so you are going to ask why you cannot decrease the price. So if they operate at this condition, which means the other 2 units will be more competitive, right? They also need to want to go up. So eventually, they reach this equilibrium at the same price. Okay. All right. Another thing I want to talk about quickly is what if you don't care about this such variables and you want to solve a really large problem with many units, and we still want to use some program, computer program to do it. So one way to do it will be the Newton-Raphson approach. So Newton-Raphson approach, we just Newton-Raphson approach is to solve an equation, but for this case, it's a linear equation. But later, when we add a power flow problem, we'll make this problem more complex. The Newton-Raphson approach, you need to give some initial guess. Even the initial guess is wrong, but after some iteration, eventually you will go to the final solution, same as what we did for power flow. Okay. So if you use Newton-Raphson approach and we want to solve lambda will be the main thing to solve. So this is actually from the power balance equation. So if the lambda is not at that $8.5, so it will not be equal to the final load. Okay, but you can iterate. So Newton-Raphson method is each iteration you can update that lambda until the gap becomes 0. So each step you can update the lambda value. So it will be still those 3 equations, but at each iteration before you stop the iteration, there will be always this one is not 0. That will be the gap between the total generation and the total load. But that gap will help you to determine how much to update the lambda. So if we try the Newton-Raphson approach to demonstrate this approach on this simple example, we start from arbitrary value. You can use any value, like $6. This is much lower than our final solution. So let's see what happens by using Newton-Raphson approach. So you plug in this lambda into the first formula. You will have 3 output. So if you do the math, the total is much less than 800, but don't worry. So the gap is huge. The gap is more than 600 as the gap. But you can use this gap to plug in the equation to calculate how much you want to update the lambda. It tells you need to update the lambda go up by 2.5. Okay. So if you visualize what happened is your first step, you arbitrarily pick a price. So there's a three line indicating the incremental cost. I don't know where I need to operate those 3 power plants. Let's arbitrarily pick a value, which is 6. Okay, so you will draw a horizontal line at 6. So they will intersect with 3 line at 3 value. So those 3 value added together is only about 100, but much less than 800. But don't worry, Newton-Raphson process, you need to go up by 2.5. Okay, then you add that 2.5 to 6. We know this is our final solution. So gap becomes 0. So that's second iteration. So only by one iteration, you'll find the same solution as we did from previous slide. Why does it take only one iteration? Because it's a linear problem. Later, if we make problem nonlinear, you need to take more iteration. Okay, so that gave you the same solution. So verily, the Newton-Raphson method just adjusts a horizontal line to move up and down until the intersections give you the total demand. I'm not requesting everybody to use the Newton-Raphson method. We just use this method to understand how we can find a solution by a number of iterations. So you start from initial guess, and you draw the line, and you can move up and down until the intersection point together give you 800, which is a PD. We'll use the same approach for a more difficult problem in next week. All right. Okay. See you on Monday.